We're going to look at some specific types of reactions that we can find the enthalpy for. One particular value we might be interested in is the standard enthalpy of combustion, which would essentially be the heat produced when 1 mole of the substance is combusted at 1 atmosphere of pressure and 25 degrees Celsius. We represent those standard conditions of temperature and pressure with a little degree symbol next to the delta HC. The subscript of C stands for combustion. We could burn carbon, for example, react it with oxygen, and turn it into CO2, and the change in enthalpy for that reaction has been measured to be negative 393.5 kilojoules per mole. You can see a variety of different substances in this table for you to refer to. Here's an example using a standard enthalpy of combustion. We're trying to figure out how much heat is produced by burning 1 liter of gasoline. We're going to assume the gasoline is basically made up of isooctane. If we look up isooctane in our table, we can find its equation and its delta H associated with it. We're also given in the problem that the density of isooctane is 0.692 grams per milliliter. To find how much heat is produced by burning 1 liter of gasoline, first we're going to change our 1 liter of isooctane into milliliters. We're changing it into milliliters so that we can use its density as a conversion factor to go from milliliters into grams. We divide by 10 to the minus 3, and that gives us 1,000 milliliters of isooctane. Then we can go from milliliters into grams using the density of isooctane. We're told the density is 0.691 grams per 1 milliliter. The word per essentially means divided by. 1,000 times 0.691 gives us 691 grams of isooctane. Then we can go from grams into moles by dividing by the molar mass of isooctane. We do 691 divided by 114.232, and that gives us 6.049 moles of isooctane. Now we can finally use our balanced equation that tells us that negative 5,461 kilojoules of heat is associated with 1 mole of isooctane. Since we don't have exactly 1 mole, we need to do a stoichiometry type of calculation. We start with the moles we actually have, 6.049, and use our known relationship as a stoichiometric factor. We do 6.049 times negative 5,461, and that gives us negative 33,034 kilojoules. By the way, this amount of energy could melt 99.2 kilograms, or in other words, 218 pounds of ice, and that's just using 1 liter of gasoline. Another special type of reaction that we're interested in the delta H for is standard enthalpy of formation. Again, the standard conditions are represented with the degree symbol. The subscript F stands for formation. The standard enthalpy of formation is the enthalpy change for a reaction when we have 1 mole of a pure substance being formed from free elements in their most stable states under standard state conditions. Several things have to be true for a reaction to correspond to a standard enthalpy of formation. The reaction must have a single product, just one thing on the right-hand side. The product has to have a coefficient of 1 because we're talking about exactly 1 mole of that substance being formed. The reactants have to be single types of elements, the way we find them in nature. For example, oxygen will be found as O2 gas, not as molecules with multiple different elements like carbon and oxygen together. The coefficients in front of the reactants may end up being fractional. In this chapter, we're going to be manipulating our equations, and as we do, we may end up with some fractional coefficients, and that's going to be okay. Rather than only having the lowest whole number ratios, we're going to make changes in order to do the calculations that we need to do. So here are some examples of equations for standard enthalpy of formation. Let's say we wanted to find the enthalpy of formation of CO2. In the equation shown, we have CO2 as our single product on the right-hand side, and it has a coefficient of 1. On the left-hand side, we have the elements that are needed to make up CO2. We have carbon and we have oxygen, and they're in their standard forms. Carbon in the Earth is found as a solid, usually as graphite, and O2 gas is how we find the oxygen. Our equation for enthalpy of formation of CO2 is carbon solid plus O2 gas makes CO2 gas. The enthalpy of formation, that is the enthalpy associated with that reaction as written, is negative 393.5 kilojoules. We can do another example with NO2. NO2 is a single product on the right-hand side, and it has a coefficient of 1 because we're finding the amount of energy needed to make 1 mole of that substance. On our left side, we have nitrogen and oxygen the way we find them in nature. Nitrogen is found as N2 gas. Oxygen is found as O2 gas. And we have the coefficients needed to make the correct number of atoms on the right-hand side. On our right-hand side, we have 2 oxygens, so our O2 molecule on the left is fine. We've got 1 nitrogen, so our N2 molecule would not be okay with a coefficient of 1. We would actually need to put a coefficient of 1/2 in front of it to indicate that we have 1 nitrogen atom. 1/2 of an N2 molecule would be 1 nitrogen atom, and that matches up with our 1 nitrogen atom on our right-hand side. These equations do still need to be balanced. They just might end up with some fractional coefficients on the left side because we're stuck with the right side having a coefficient of 1. The enthalpy of formation of NO2 ends up being a positive 33.2 kilojoules. Let's practice writing enthalpy of formation equations. Here we're writing the equation for C2H5OH, which is ethanol. We need to have the thing we're trying to form on our right-hand side as our only product with a coefficient of 1. On our left side, we need to have the elements that are needed to make it up. In this example, we're going to have carbon, hydrogen, and oxygen in their elemental forms the way we find them in nature. Carbon is going to be solid graphite, hydrogen is going to be found as H2 gas, and oxygen is going to be found as O2 gas. As you do these types of problems, you're going to get a sense for what the elemental forms are that each of these elements comes in. We also need to make sure that our equation is balanced, without changing the coefficient of 1 on the right side. On our right side, we have 2 carbons, 6 hydrogens, and 1 oxygen. So on our left side, we're also going to need to have a total of 2 carbons, 6 hydrogens, and 1 oxygen. However, we're stuck with the particular ways of writing each element. If we want 2 carbons, we can just put a 2 in front of our carbon solid graphite. If we want 6 hydrogens, we can put a 3 in front of our H2 gas, since 3 times 2 gives us 6. If we want 1 oxygen, we're going to have to put a 1/2 in front of our O2 gas. 1/2 times 2 gives us 1, which matches up with the 1 we have on the right-hand side. Our equation for the enthalpy of formation of ethanol is 2 carbon solid graphite plus 3 H2 gas plus 1/2 O2 gas makes ethanol. Sometimes we'll be given an equation, and we'll want to manipulate it to get it into the correct form. Our enthalpy of formation reactions have a very specific form that they need to be in order for it to count as an enthalpy of formation. In this example, we have a reaction of 3 O2 gas going to 2 O3 gas, and the delta H for that reaction is 286 kilojoules. We are asked to find the delta HF, enthalpy of formation, of ozone. We need ozone to have a coefficient of 1 in front of it in order for it to be a true enthalpy of formation reaction equation. What we're going to do is divide our whole equation by 2, which means each of the coefficients in the equation get divided by 2. 3 divided by 2 gives us 3/2, and 2 divided by 2 gives us 1. We end up with a coefficient of 3/2 in front of the O2 molecule and a coefficient of 1 in front of the ozone. We've gotten our equation into the proper form where we have a single product on the right-hand side with a coefficient of 1, and then an element on our left-hand side in its elemental form the way we find it in nature. Since we divided the equation by 2, we also must divide our delta H by 2. 286 divided by 2 is 143 kilojoules as the enthalpy of formation of ozone.